Hi students, welcome back. This is lesson D. Well, lesson 15, video, part D here. In the last video, Kim Shepard did 2 complete examples, start to finish. So we're getting good at confidence intervals, and now it's time to learn a bunch of important facts. Okay, so that's what the point of this video is here. And there's 8 of them, and we'll go through them, and this will really help to develop our understanding of the ideas behind these confidence intervals. Fact number 1, top of the page, the parameter that we're estimating, and remember a parameter is a number that describes a whole population. In this lesson, we're talking population proportions. So every time we do a confidence interval, we're basically trying to estimate a whole population's proportion. Like what's the proportion of all people in Maryland who are compulsive gamblers? The parameter doesn't vary. That's a fixed number. Okay? And even after we collect our sample, we still won't know its true value. There are about 5 million people in Maryland. We took a sample of 1,200. Once we've collected that data, we still don't know the true proportion of compulsive gamblers in Maryland. So what could we say about the parameter? Its value is fixed. Right? At the time of our data collection, that value is fixed, and it's also unknown. Parameters start with P, they describe the population, starts with P, fixed and unknown. All right, so there's an example. We'll go back to this compulsive gambling. Back in the last video with Kim, we estimated the proportion of Maryland adults who are compulsive gamblers. And like I said, even after we collected our data from 1,200 adults, we still don't know the true proportion for all adults in the entire state. Okay? We'd have to collect data from millions of people to obtain that value. There are over 5 million people who live in Maryland. There are probably over 4 million adults. All right? To get the true value, we would have to collect all that data, and it's just not realistic to do it. Okay, fact number 2. Pretend you were going to take another sample, which typically we don't do. In statistics, we try to collect the single best sample we can get our hands on. Let's say we did collect another sample. What would happen? Certainly we would get different data, which certainly would result in a different confidence interval. You have to understand that our confidence intervals are random. If you take another random sample, then the result is going to be another random confidence interval. And keep going. You'll get confidence intervals sort of bouncing around. You like line them up and they'll be moving. Okay? Well, the single confidence interval that we got is based on the random sample that we happen to collect, all right, during the data gathering process. All right, so if we flip down, I think we've got an example of this. We'll go back to this compulsive gambling. Remember, we created that 99% confidence interval. What had happened was we had 15 compulsive gamblers out of 1,200 people. That interval ended up being about 0.42% up to about 2.08%. For the whole state. That'd be our conclusion. Well, take another random sample. This time we get 25 compulsive gamblers. You should check at home that you can get this interval. It's still a 99% confidence interval, but here's the answer at this point. It's about 1.021% up to 3.145%. Different data, different interval. Right? In practice, we're just going to take one sample and use it to the best of our statistical abilities. Remember, we're never sure. In the whole rest of the course, you're taking a little piece of the whole pie and making conclusions. You'll never be 100% sure of your conclusions. There'll always be a little bit of uncertainty. But we try to minimize it, and we can live with the results that we can get. All right, that was 2. Let's go to 3 here. Let's talk about what the word confidence actually means. You might expect it to be a probability, but it's technically not. Okay, here's what it is. If we took repeated samples of 1,200 adults in Maryland, go again, just keep doing this thousands of times. Confidence level is the proportion of those intervals that would actually contain the true number, right? It's the proportion of intervals that would actually contain the parameter we're estimating if we took many, many repeated samples, which we won't. I'm going to draw a horrible rendition here of the state of Maryland. It's going to do something. I don't know what this is, but this is Maryland. It definitely needs to be labeled. All right, here's Maryland. Population in Maryland, about 5 million people. And a certain percentage of the whole state are compulsive gamblers. That would be called P. P is the percentage of all people with gambling problems. When I take my interval is either going to hit the target, and the target is that number P, it's the true number, or my interval is going to miss it. I don't know if it's going to hit or miss. I'm 99% confident it hits, but at the end of the day, I wouldn't know if mine actually hit it or not. And if I kept creating more and more intervals, then about 99% of them would hit the target in the very long run. That's the idea of confidence. Okay? It's not a probability. Like, what's the probability that my interval hit the target? It's technically not that. All right. I've done better with my pictures, so I better get rid of this. And at the bottom of that page, suppose in Maryland that it's 2%. I don't know that it is. I made that up, but just suppose it's 2%. All adults are compulsive gamblers. When we take a sample, most of our intervals would contain that target 2%. A few of them won't. And again, if we're choosing a 99% interval, then in the long run, this is an easy fill in the blank here. 99% will hit the target. 1% will miss. Unfortunately, at the bottom here, we won't know if our particular one interval actually hits or misses. And the best we can say is that, hey, I'm 99% confident that my interval hits the parameter that we're trying to estimate. Okay, so that's the end of that page. Only 3 more to go. Pages, not numbers on this video. Fact number 4. Think about this. The more confident you need to be, the more confident you need to be of actually hitting the parameter. What do you need to do? You need to purposefully make your interval wider, right? A wider interval will have a better chance of hitting the target. So the more confident you need to be of containing the parameter you're estimating, the wider we must purposefully make the interval. We're consciously saying, let's make it wider. And so how can I do that? We can change the confidence level, right? And think about it. If I want to crank the confidence level up from, say, 95 to 99%, something's going to change in that formula that should make it here and then go out to 99% a little bit wider. All right? So, what can I change? The answer is that number z. That's the critical value. And remember 2 videos ago, if we wanted to be 95% confident there was a certain z number, happened to be 1.996, excuse me. If we wanted to be 99% confident, it was bigger. More confident, it was 2.576. Okay? So we can change the z consciously. Example. Back to we're talking about compulsive gambling. Well, let's talk about guns for just a second here. The Cecil County gun ownership example, where, remember in Mother Jones magazine had said a certain percentage of houses in the country own guns. And then we made up some data. And we said, well, pretend, who knows what the case is in Cecil County. But we said pretend that we had 300 out of 400 homes in the county. Owned guns, do the confidence interval. It was the opening example of the whole unit. And the 95% interval happened to be this. And now, real quick, we'll get it on the board. What if instead the question said, I need to be 99% confident? If this is my 95, my 99 will be here, because I'm going to jump out a little bit more, a couple more standard errors, a little bit extra on both sides. So, Remember, let's just see this quickly. 95% gave me a z of 1.96. And we've already done this, so I'm just going to repeat it here. A 99%er would give me a z of 2.576. When I plug into my margin of error, the 2576, it'll make the margin of error bigger. So let me get that on the board here. Let's see. Just go right to the numbers. P hat, remember, is still 0.75. That's the 300 out of 400. So the interval will look like this, students. 0.75, that's my p hat. Plus or minus, the z comes next. It's a 2576 times that big square root. 0.75, 1 minus 0.75 is 0.25. And we had 400 residents or households. So the formula will look like that. It turns out to be 0.75 plus or minus about a 0.558. And if I cut to the chase, I'll skip the decimals, I'll go right to percentages. That interval will be 69.42% all the way up to 80.58%. And so for whatever reason, if I needed to be more confident, 99% instead of 95, just look at the difference. This one goes about 70.8 up to 79.2, and now this one is 69.4 up to 80.6. A little bit wider. All right? So we've got that. Takes us to number 5. All right, let's see what we're talking about with number 5 here. Oh, margin of error. All that stuff to the right-hand side of the plus minus, that quantity. In this case, it was z times that big square root, which was standard error. That quantity is called margin of error. So we're doing p hat plus or minus margin of error, right? That's that whole thing. We would like margin of error to be what? Big or small? Just think common sense. I prefer margin of error to be small, right? Sounds like accuracy. Sounds like my interval will be skinny, which might be a good thing. We'd like margin of error to be small, because the result will be what? The intervals will be skinnier. I'm adding and subtracting a smaller number, so my intervals will be skinny. Let's give the formula for margin of error for a confidence interval for one proportion. Let me see here. Just going to slide backwards a slide for more white space. We're still at the bottom of that page, but margin of error here, so just ME for margin of error, is the right-hand side. So we've got the z number, and then times big square root p hat 1 minus p hat all over n, whole thing square rooted. Okay, so down at the bottom of 5 there, it says give the formula. Here it is, margin of error equals. Okay, and now we might ask our question, if I wanted to affect the value of margin of error, can I change some things? Can I do a few things to, and you can see, maybe sample size is in our control. Maybe we could collect more data, for example. Or maybe we can live with less data. We sort of hinted already, can I change the confidence level? I think I can, that's a z. P hat here, that's the sample proportion. Not so sure that we can actually affect that, because that's going to come from the collected data. So it looks like 2 out of 3 things we might be able to affect. All right, so we'll flip the page. You've got that formula. I got to erase it to clean this up. And let's see. Oh, you can see from the formula, margin of error is certainly based on 3 quantities. Margin of error depends on, well, p P hat was in the formula, Z was in the formula, and N was in the formula. Like I said, we can't change P hat. That comes from the data. People are either compulsive gamblers or they're not. Right? People either have guns in their homes or they don't. I can't really affect that unless I cheat, and we're not going to cheat. Bottom bullet point here, we can change the sample size by collecting more or less data. In a classroom setting, your instructors, I remember sitting in statistics classes, like, oh, just collect more data. Once you leave the classroom setting, that's not so easy. Like, it sounds good, right? And why isn't it so easy? This is be advised here, collecting data takes time. Collecting data costs money. You certainly can always collect more data as long as you have the resources to do it. So I don't want to pretend like this is just the fix-all, like, oh, just go get some more data, because it's certainly not the case. This is, you got to put the legwork in here and spend some money. Next up, let's see what we've got here. If you increase the sample size, what happens to margin of error? Common sense should tell us that more data is a good thing. And what do we want? We'd like margin of error to be small, so let's see that it works out that way. All right, here's the formula. Margin of error equals the Z times the big square root P hat 1 minus P hat all over N. If I make N bigger, it's in the denominator. When you make a number bigger in the denominator, the result is that the whole quantity gets smaller, all right? Just think of going from, say, like, oh, simple, tiny example here just popped in my head. If I go from 1/2 to 1/9, right? I'm making the denominator bigger. This is a smaller number than this. And the same thing will happen here. If N gets bigger, as we hope, margin of error gets smaller. Right? That's a good thing. Just a costly thing, that's all. All right. And by the way, margin of error getting smaller means skinnier intervals. It follows directly, but I will write it down. We're new at this. The result of this is skinnier intervals. Skinnier intervals. This is a good thing. All right. Poking our way through this, looks like, oh, something at the bottom there. I'll move on. You can always pause the video if you need to. I know this might be my record. It feels like we're 45 minutes long or something here. I don't know. Bottom of the page. We already learned we can change the confidence level if we need to be more confident. 90 up to 95. 95 up to 96, up to 98, 99, whatever. If we need to be more confident in the interval, the margin of error will get bigger, wider. Well, the correct word here might be larger, right? Margin of error is just a number. It doesn't get skinnier, or it gets larger. If we can live with less confidence, margin of error will get smaller, right? Margin of error will get smaller. It says again, look to the formula. Let me see what I was thinking. Oh yeah, so real quick, it's good practice. But here, margin of error was that Z number, P hat 1 minus P hat all over N. And I'll just recreate the table here. Confidence, the common ones are 90, 95. Oh, I ran out of room here, 99. Those are the three common ones. And what the heck would the Z number be? The Z is telling me, oh, if I can live with being 90% confident, how many standard errors do I jump out? Typically, that one's given as 1.645. Now, I need to be more confident it jumps to 196, and I need to be extra confident it jumps all the way to 2.576. We're centering our interval at P hat, and based on confidence, this is telling me how many standard errors to jump out. If you squeeze something in between 90 and 95, the z will be in between these two numbers here. Okay? And it's sort of like, what can you live with? Two most common in practice, 95 and 99. All right, one more page. Couple more facts. Number 6. Kind of why do we do this? We can make conclusions about the whole population. That's the point. We're interested in the population. Not necessarily what the sample told us, but how can I generalize? We can make conclusions about the population based on our sample and the confidence interval we calculated from the sample. This is called inference, this whole sentence here. Here's what you do, and Kim did it in the video about the physical education building. Check to see if that population parameter of interest either falls inside or outside of the interval. For the gym example, I think administrators at Cecil College said we hope for 25% using the gym. The interval was way below 25%, the whole interval, we make one conclusion. All right, here's an example back to the guns. Remember, we made this one up. It's so clear, just so we get the idea. In the lesson 15 opening example, that was that Mother Jones magazine reported whole country, 45% of households contain guns. We invented this fake confidence interval. The 95% confidence interval from 400 Cecil homes turned out to be, 70 point whatever up to 79. It doesn't matter. The point is it's so far above 45% that we have overwhelming evidence that things are different here in Cecil, and certainly we have a higher gun ownership rate, right? That's what we could conclude. Statistically, we could conclude this and feel good about the conclusion. Whole interval. Whole interval is well above 45%. That's the national figure reported by the magazine. We have overwhelming evidence. It's overwhelming because I made it up. I said 300, but we have overwhelming evidence. The gun ownership rate is higher in Cecil County. I mean, how could you conclude anything else, right? At least based on the fake data that we made up. All right. Well, I hope. Yep. Counterexample. Opposite case. Back to the compulsive gamblers. For the compulsive gambling problem, we had found a previous study that said 1.2% of all adults are compulsive gamblers. Then we collected some data here in Maryland. And let's ask the question, is there any evidence that Maryland sort of differs from the rest of the country? The key number we're looking for is 1.2%. Our 99% confidence interval for Maryland was 0.42% up to 2.08%. What can we conclude about Marylanders with respect? Since the 1.2% is inside, I don't care where it falls inside. Smack dab in the middle, very close to the edge, doesn't matter. Let's see here, what are we going to say? Since the 1.2% falls inside the interval, the data collected in Maryland, there's no evidence that Maryland differs from the rest of the country. Right? Since the 1.2% falls inside the interval, there is no evidence. Maryland, MD, differs from the rest of the country. It's kind of an in or out proposition. Is the value in question in or out of the interval? All right. It does bring me to two last points here. I kind of want to do point 8 first, and I'm gonna skip to 8 and go back to 7. What the thought in my head is, well, what if I start fiddling with the confidence level to make my interval wider or skinnier so that I can say what I want to say anyhow? That doesn't sound very ethical or moral, right? And so we'll skip to 8, we'll come back to 7. If I was rewriting the notes today, I'd put them in a different order, but sort of permanently here it comes. If you're making conclusions about a population with a confidence interval, do not fiddle with the confidence level to be able to make the conclusion. There's an order to things. You're supposed to pick your confidence level first. Sort of plan it out. Now collect your data, next or second or whatever you want to say here. And finally make your conclusion. If you didn't get the conclusion that you want, so be it. Right? You have to realize, what's the data trying to tell you? Right? And what did you pick for your confidence level? All right, that was 8. Back to 7 to wrap it up. Main point, always make your concluding remark a statement about the whole population. Whole rest of the course, we're doing statistical inference. We're using a sample to make conclusions about the larger group of the population. All right? So, we've learned all the theory about how to construct intervals, how to interpret them, and so on. And to wrap up the lesson, Kim's going to come back. At the beginning of a problem, maybe you ask yourself the question, how much data do I need to create this confidence interval to meet my needs? And so Kim's going to come back, talk about sample size, and that will wrap up lesson 15. So, thanks for watching. We'll see you in class.